আমি ওকে বললাম তখন
Okay, we're at the top of the hour now. It looks like people are still coming in. Sayantani, do you want us to start now or wait another minute?
Yeah, let's start from now. It's already 3:02, so yeah.
Okay, sounds good. Well, hello everybody, and welcome to our live tour. I'm Mara Johnson-Grow, and I'm the Outreach Officer for Expedition 396. And I'm going to give you a brief overview of the JOIDES resolution and the program it sails under IODP before passing you off to our onboard scientists who will give you a live tour and tell you a bit more about what the expedition does and what kind of science they're looking at. So the JOIDES resolution sails as the International Ocean Discovery Program, or IODP. And this is an ocean drilling program that has gone back to the 1960s was the first drilling it did. It's an international collaboration built under US funding from the National Science Foundation. And it goes all around the world to collect cores that are then stored in 3 repositories based on where they were drilled from. It's already gone on for 80 years, and it plans to continue much longer. Our new science framework was recently announced, where we want to continue this research and exploration, where we're looking at Earth's history across time, and then communicating our findings. So the ship itself looks like this. It's a huge 470-foot vessel that we've had for several decades and was recently retrofitted. And aboard this ship is where all the drilling takes place. So we'll get a tour of that in a little bit. But what we're doing essentially is taking core out of the bottom of the ocean. So here are some of these cores that have been sampled previously. And what we're doing is taking these and doing all sorts of analysis, looking at different properties and things that we find in them to sort of understand Earth's history better. And so, as I mentioned previously, the ship has sailed all around the world. These dots each represent a different expedition location. Over the years, the IOD program was predecessed by a few different other programs, so that's what the colors represent. But as you can see, there are literally hundreds of sites that we've been to. So currently, we're floating off the coast of Norway up in the North Atlantic, left at the port in Reykjavik, Iceland at the beginning of August, and we'll shortly be concluding the trip in Norway. But for now, we're above the Arctic Circle, floating and sampling some core samples. So this expedition is called the Mid-Norwegian Continental Margin Magnetism. And essentially what we're looking at, and Sayantani will go over this in greater detail, but we're looking at this place that has a lot of excess magma deposits. And so we're looking at how that excess magma is linked to past climate change events, and sort of how learning about that, how we can draw insights for the current climate change that's affecting our planet currently. And along with that, the possibility of even storing the carbon emissions that we produce under the oceans in some of these locations. So with that, I will pass us over to our onboard scientist, Sayantani Chatterjee, and I'll let her take it from here.
Yeah, thank you so much, Mara. Good afternoon and good morning to everyone. I'm Sayantani Chatterjee, postdoctoral researcher in Niigata University, Japan. I'm participating as an inorganic geochemist in Expedition 396. So before doing the ship tour, I want to give you guys a quick introduction about what we are going to do and how we are going to do today. So here I will just share my screen. Mara, can you please help me to share my screen? Uh-oh. Mara, can you please allow me to share my screen?
Yeah, sorry, I'm having a few changes here. Just 1 second.
Yeah, sure.
Okay, you should be able to share now?
Yes, I think, yeah. Can you see my screen?
I'm not seeing it yet.
Nothing. Screen. Just a moment. What is happening? Can you share? Can you see it now? No?
Still not seeing it.
Okay.
Okay.
I think
there we
now
go.
you can. Yeah. Just a moment. I will just open presentation. So here's, yeah. Right. So as Mara already explained about 396, that we are right now at Norwegian Sea or North Atlantic Ocean. So just above the Arctic Circle. So this is the real image of JR on your right. So it's taken by Peter, one of our onboard scientists. So now if we see closely on JR, so today I will start, I will try to cover maximum of the area, and we'll start from the bridge deck. and from where you can see the derrick, and then we will continue, go downstairs to see all the labs, starting from core lab and then paleomag lab, then biostratigraphy lab, geochem lab, and then we will go downstairs again and we will see our hello, somebody is can you please mute your Zoom session? Thank you. Okay, and after that we will I will show you the other facilities like gym and our movie room, and if time permits then I will go to I will go to our quarters to give you a quick tour in our accommodation. So after all of this I will come back again to the bridge deck, and there we will have a discussion with our co-chief and our staff scientist, and we will take all of your questions after our ship tour. And as you know that this program, this outreach program is conducted by IODP, and we are co-hosted this program with GGDC Manbajar Purulia College, and we have our students from all over the West Bengal and also some other parts of India. So yeah, let's start the tour now. I will stop the screen sharing. Just a moment. Yeah. Yeah. So do you have any question or queries before I start the tour? You can ask.
Sayantani, am I audible?
Yeah.
Okay, I have a request. If you can just give the description of this tour in both Bengali and English, it will be probably helpful to many of our young audiences, because many of them are from rural parts of Bengal. It will be great.
Yeah, sure, Arnab. I will do that. Okay. I will try it. So before going outside, আমি সব স্টুডেন্টদেরকে বলতে চাই যে তোমাদের যদি কোনো প্রশ্ন থাকে তোমরা জিজ্ঞেস করো। কারোর যদি যে কোনো মুহূর্তে যদি কোনো প্রশ্ন থাকে তোমরা জিজ্ঞেস করো ইন এনি ল্যাঙ্গুয়েজ, আমি চেষ্টা করব সেটা উত্তর দেওয়ার। আর যদি মনে হয় যে খুব ফাস্ট আমি বলছি বা কিছু, তাহলে প্লিজ আমাকে বলো সেটা। সো let's start it from here. Okay. Let's go outside. এটা আমাদের ডেরিক, এখানে এই স্ট্রিমটা এটা নিচে 3000 মিটার ডাউন ওয়াটার ডেপথে এখন ব্রিজ করছে, and we already recovered around 350 meters of core, সেটাতে 200 meters of sediment আর around 100 meters of hard rock basalt আমরা already recover করে ফেলেছি। Similarly, আমাদের লাইফ পোর্ট নাম্বার 1 and 3 অপোজিট সাইডে আছে। আর তোমাদের একটা গ্লান্স দেখিয়ে দিচ্ছি আমাদের নরওয়েজিয়ান সি এর, যদিও আজকে ওয়েদার খুব ভালো, জেনারেলি এরকম ওয়েদার থাকে না। Some couple of friends. এইগুলো হচ্ছে ড্রিল পাইপস, যেগুলো ডাইরেক্টলি এই জায়গাটাতে যায় এবং গিয়ে ওইখান থেকে ড্রিলিংটা স্টার্ট হয়। ড্রিল হওয়ার পরে এই যে জায়গাটা আছে এখানে আমাদের কোর যেগুলো রিকভার হয় সেগুলো আসে, এটাকে বলা হয় ক্যাটওয়াক। তো এই ব্রিজ ডেকের পরে আমরা যাব ক্যাটওয়াকে এবং এখানে আমরা দেখবো যে কিভাবে অপারেশনটা হয়। So yeah, let's go inside. Okay, so আমরা নিচে যাব, নিচে আমরা 4 ডেকে যাব। আমাদের সুন্দর একটা পেট ওয়াল আছে, এটা সবাই নিজেদের পেটদের ছবি এখানে রেখেছে। So I know. Can you visit the catwalk? Stunning. Safe classes. Yep. Yes. এটা আমরা একটু আগে দেখলাম, ডেরিক থেকে যখন পোর্ট রিট্রিভ হয় তখন এখানে আমাদের টেকনিশিয়ানরা পোর্ট নিয়ে আসে, এখান থেকে এসে আমাদের পোর্ট 1 মিটার লেন্থ অনুযায়ী সেটাকে স্প্লিট করা হয়, তারপরে সেটা নিয়ে আসা হয় পোর্ট এই রুম। Now Rose will explain you the operation in the catwalk.
Hello, I'm Rose. I'm one of the technicians. And the way this works is that this is the drill floor. This is where the floor comes from. Down in a long pipe. All the way down. Carry on. Up down here. This is one of the core liners. So in here, but it's quite valuable, and you never know, even in the tree of the pieces, it could be valuable. It's all inside. Then, when it comes in here, we carefully take it into this. Here. So we will take these cores in here, we'll measure them and make sure we're confident in our rotation and how much material we have. And then they will either go out into the thorax outside, so you can go through the door, you'll be able to see them there. Yeah, this here. And we will, if they're rocks, put them together carefully. We'll make sure we know exactly each curve, each little piece, which way round it goes, and which order they go in and whether they fit together. Sometimes they come out in pieces and we have to fit them together like a puzzle. And in that case, we will then put little labels on and lay them out as you see here.
First thing we have to do all the stickers and
All the stickers. So you should find a piece with a sticker on. Here we go. You see we have the little sticker. And that way we know where everything has come from, and if it's this
which
way up
piece
or
is
this way?
which piece, right? And we can see that there is one mark on W. And
Yes.
what does that mean?
This means this is the working half. So Sayantani and all the scientists will come in and they want to sample. This is where they'll take it from.
And then Brittany,
Okay.
can you explain us how you guys split the core and what is the working half and what is the archive half?
Yeah, so once the core makes its way through the lab, and all the measurements are done on the whole round, we bring all the sections into the splitting room to be split in half. So one half is the archive half that's untouched for at least 10 years so that people like you or people who come back in the future can look at these cores. And then the working half is to do destructive analysis. So we'll take samples from the working half. With soft sediment, we are able to use a cheese wire type of splitting over hard rock that we're getting. We've been using this rock saw to split the sections in half.
Okay, thank you so much, Brittany. তো আমি এখানে একটা জিনিস অ্যাড করতে চাই। এখানে আমরা দেখলাম ওয়ার্কিং হাফ রয়েছে আর আর্কাইভ হাফ রয়েছে। আর্কাইভ হাফ যেটা সেই জিনিস সেই স্প্লিট কোর গুলোকে আমরা টাচ করি না 10 ইয়ার্স। ওয়ার্কিং হাফ যেটা সেখান থেকে আমরা নিজেদের পার্সোনাল স্যাম্পলিং, শিপবোর্ড স্যাম্পলিং এগুলো কালেক্ট করতে পারি। তো এবার প্রশ্ন হচ্ছে এত পরিমাণ যে আমাদের কোর আছে সেগুলো থাকে কোথায়? শিপে তো থাকার উপায় নেই। তো আইওডিপির 3টে রিপোজিটরি আছে, তার মধ্যে একটা হচ্ছে ব্রেমেন, জার্মানি, নেক্সট হচ্ছে টেক্সাস, আর আরেকটা হচ্ছে জাপান, কোচি। এই 3টে রিপোজিটরি সেন্টারে এই সব ওয়ার্কিং হাফ গুলো যায় এবং আফটার লাইক 6 মান্থ আমাদের এই পোস্ট ক্রুজ একটা মিটিং হয়, সেখানে প্রত্যেককে যায় এবং তাদের পার্সোনাল স্যাম্পলিং কালেক্ট করে। এবার এটা ডিপেন্ড করছে কোন ওশনে আমরা ড্রিলিং করছি আর তারপরে সেটা কোনখানে কোন রিপোজিটরিতে যাবে। জাস্ট লাইক যদি আমরা ড্রিলিংটা জাপান সিতে করি বা প্যাসিফিক ওশনে করি তাহলে সেই ওয়ার্কিং হাফটা আমার যাবে হচ্ছে কোচি রিপোজিটরি সেন্টারে। এইখানে আমরা যেটা করছি নর্থ আটলান্টিক হুইচ ইজ ভেরি নিয়ার টু ইউরোপ, তো সেই কারণে আমাদের এই ওয়ার্কিং হাউস গুলো যাবে ব্রেমেন, জার্মানিতে। তো আফটার 6 মান্থ অ্যারাউন্ড এপ্রিল আমাদের যারা শিপবোর্ড সায়েন্টিস্ট আছে আর যারা শোর বেসড সায়েন্টিস্ট আছে প্রত্যেকে সেখানে যাবে এবং গিয়ে তাদের নিজেদের রিসার্চের জন্য তারা নিজেরা স্যাম্পল সিলেক্ট করবে। তো ওকে, এখানে আমাদের ছোট যে পিসেস গুলো যেগুলো আমরা শিপবোর্ড স্যাম্পল যেগুলো কালেক্ট করি সেগুলো এখানে পিসেস কাটা হয়, লাইক to take thin sections or যদি আমরা XRF analysis করতে চাই তাহলে তার জন্য 5 to 6 সেন্টিমিটার কিউবের স্যাম্পল লাগে। তো সেগুলো আমরা এখানে আমাদের টেকনিশিয়ানরা হেল্প করে সেগুলো কালেক্ট করার জন্য। ওকে,
Hello, everybody.
so Dustin is here. He is a sedimentologist and so that women, and they are here in a core description group. So Dustin, can you explain us about something sedimentary stuff?
Yeah, sure. So we have a nice sediment core that we recovered at the latest site, and it has some examples of what we might see in these marine sediments. We have really nice laminations at the top, millimeter scale, and you see these alternating colors, and it's likely related to compositional differences. So whether that's the amount of organic matter in the material. Some of these organic rich beds are also pyritized, so you can see these golden intervals here. And we also have some other nodules of pyrite here, so a nice golden, shiny nodule. There's a bit of structural deformation also happening through some of these laminations. You can see that some of them are slightly offset, and that's the consequence of compression, extension, a variety of deformational stresses that these rocks might undergo after they've been buried. We also have some hard rocks, but I'll leave that to the Sayantani to
Or maybe Sarah can
maybe
explain.
Sarah
Yeah.
wants to come. But this is a hyaloclastite, so this is a shallow water. Hey Sarah, you want to come explain some of the hard rocks? So I don't say the wrong things. I just pointed out the hyaloclastite.
Hello.
And
I'm Sarah Nobel, assistant professor at the University of Utah. Yeah, so we have good example of hard rock here. So here we have what we call a yellow clastite. So a yellow clastite is typical of interaction between lava and water and sediments. So you see how angular those blocks are. It's because when you have lava entering into the water, the process is quite violent, and so you fragment the lava and you quench it. So that means that it's cooled down very, very quickly, and you get these very angular blocks of basalt in the middle of the sediments here. And here we have actually a spectacular example of what we call a kilo lava. So again, when the lava is entering into water, if the water depth is a little bit deeper and you have more water pressure, the process is going to be less violent, and instead of having something fragmented like that, you will form what a ball of basalt, basically, that is typical of submarine eruption. And here we have a typical example of this pillow lava, where we have a glassy margin, so the lava is completely quenched instantaneously, so you preserve this glass that was initially a lava, basically. And on top of that, you have these pipe vesicles and these radial fractures that are basically typical of the formation of the balls that is preserved in a pillow lava.
Yeah. Can you show us some thin section of the basalt?
Absolutely. You must have noticed that those rocks, when you look at them like that, they look relatively homogeneous. We don't actually see any grain, but we still need to identify the mineralogy, because the mineralogy is going to give us information about what kind of rock melted, what was the processes that actually resulted in the creation of this rock. So, because we can't see anything in hand samples, what we do is we use the photographic microscopes. So we look at rocks using this microscope. So I can show you an example here. So here we have a very nice example of these sections, and so this is a basaltic andesite, and you can see that we have large plagioclase crystals here. To give you an idea, this is about half of a millimeter, and so we have large plagioclase crystals. We have angular vesicles that are completely filled with saponite, so it's a secondary process that fills the vesicles, so the vesicle with alteration mineral. And we can actually use the special tools that we have on petrographic microscope, which is a second polarizer, to even identify more minerals. So I'm going to show you here. And so now you can see that we have actually different type of mineral in this section. We have large plagioclase that shows this prismatic habit. And we also have these minerals that show very, very, very vivid color with this second tool. And so those are actually clinocurcell. So we have a matrix that is mostly composed of clinocurcell and plagioclase. So I should have started with that, but what we are looking at right now is what we call a thin section. So it looks like that. Okay. And it's a very, very thin slice of rock that is stick to this piece of glass, basically. And so to give you an idea of how thin it is, it's 30 microns. So a single hair is, in average, 50 microns. So it's thinner than a single hair. And so that's why we can actually see these crystals under the microscope, because now it is so thin that the light can actually go through. And so that's very useful when the grain size is so small that you can't see anything in hand samples to actually complement your description in this petrographic description.
Thank you so much, Sarah. So next we will go to the physical property, and here we have John. Can you explain something about physical property and what is the workflow here?
Yeah, indeed. So basically, I work in physical properties also with Irina, who's currently holding the camera. So basically, what our job is to measure different types of physical properties of the different rock cores. So things that we're measuring are things like density, so how heavy the rocks are basically. We measure the velocity, so the sound velocity, how quick the sound can travel through, or sound waves can travel through the rocks. And we also measure properties like the magnetic properties and also the porosity. So a bit of context for you. So again, you've just heard from Sarah about some of the nice volcanic rocks that we've been drilling on this cruise. So again, from 2 or 3 kilometers under the ocean, we're pulling out things like this. I don't know if you can see that. So all of these holes here in this lava sample were gas bubbles, basically. So when this was erupted as a lava at the surface, so it's quite an interesting thought to think that this at one point was about 55 million years ago, was at the surface as a lava flow. And so what we do is we take little mini cubes of this, and I've got a few examples here. So we cut little mini cores or mini cubes, and you can see some of these with these nice pore space in it. And then we measure them for porosity, so we find out how many or what's the volume of the rock that we have in this pore space. And the reason that we're looking at that is to try and see if we can understand about putting carbon capture back into it, so putting CO2 back into the rocks. And then we've had a whole range of different rock types on this cruise. So here's an example of granite. So we've had granites, we've had basalts. And the reason these are very different, so again, this is what Irina's speciality is looking at the differences in density. There's a reason that the seafloor under our feet is so deep, is because it's actually very dense. It's made of this dense basalt material, which is about 3 to 3.1 grams per cubic centimeter, whereas the granites are about 2.6, 2.7. So again, the different densities of the crust depends on, dictates whether things move up and down as the continents move apart. And the reason we like the velocity, so I don't know if you can see on the screen behind us here. So we're currently measuring a sample over there. We've got it between 2 sensors. These 2 sensors are sending a sound wave through this rock sample here. What we do is we see the signal here, and it measures the time before we get that sound signal coming through. We can use that to see how fast the rock is. The reason that's important is that if you look at these kind of nice seismic lines where they've sent a boat doing surveys for these, basically sending sound waves down and receivers to find out what's going on. You get this nice image of 2D, which looks a bit scattered, but then when you do your trigonometry and you put these things back together and look at all the different angles and the time it takes for the sound wave to reach these different parts, we can actually pick out these beautiful things like lava flows coming down, cascading down this paleoescarpment. It looks like something you'd find on modern day Hawaii, but it's actually about half a kilometer under the sea bed. So that's the kind of things that we're doing.
So these are only for hard rocks, and how do you explain sediments?
So the sediments we have to deal with a little bit differently. So where we can get, as you say, we can get a nice sample, we deal with the hard rocks. When it's soft samples, what we do is far less fun, because I prefer volcanic rocks, as everybody does.
Yes.
So what we do is we take this syringe, and so I'm not going to do it now, but basically we put the syringe into the sample, take a cylinder of the sample, and then put it into these jars. And these jars are pre-weighed in the laboratory beforehand. So we put them in, we measure the densities, and then so I can show you some examples here of cylinders. So you can kind of see in there this small cylinder of rock. And so we use that, we measure the wet density, then we dry it in the oven overnight. So Irina calls it a baking. So we get rid of all of the fluids in it and measure the difference, and that tells us how much pore space there is. So that's how we deal with the sediments. We have to deal with the sediments because they're there, and of course they're very interesting scientifically. But for me, I stick to these nice samples of lava flow. So.
Thank you so much, John.
Okay.
So next we will go to the Paleomet group. So Natalia is in our paleomagnetism group, and she is the only one who is responsible for all the magnetic fields. So, can you explain a little bit about what you are doing?
Yes, of course. So here in BMAP, what we do, we try to build an age model based on the different magnetic reversals over time. As you know, the Earth is a big magnet, and this magnet right now has the geographic north aligned with the magnetic north, right? So that would be our normal state. But over time, in geological time, we have to switch back and forth toward the south and north. And that is very, very well
the recent sites that we were just working on. For that, we use scores and we use the cubes that I just don't want right now with me, but we use all this very high-tech equipment to kind of figure out what is actual information.
Thank you so much. Okay, and now we will go to the biostat group.
Biostat group,
Yes.
that's particularly in this shift, it's Rick Shearer, ladies and gentlemen. And it's Hank Brinkas on the other side.
And the best view on the ship is in the Paleo Lab.
Oh, yeah, that's for sure.
So that shows you how important fossils are. And they give us the best view. So hi, I'm Reed Scherer. I'm from Northern Illinois University in the central part of the U.S. And the cores that you've already seen, when they're sediment, we break them. It starts off as rather ugly looking mud, and we break them down, and then we put them on microscope slides to have a look in the microscope. And there you see a wondrous beauty of these microscopic little fossils. So let's go have a look.
Sure. We have a good one here.
Yes, and we love our families and we love our pets, but we also love food that we miss. So we have this here to remember some of the foods that we have when we get back home again after 2 months on board. So this is where the paleontologists work. And notice how many chairs we have, but it's just Hank and me because we have a smaller team than usual, but there are no shortage of fossils to look at. Now, why don't we first start down over here? This is our board where we keep track of what the ages are, because the fossils can tell us something about how old the sediment is. And we look at a lot of different groups. So the group that I look at is a group called diatoms. They make their shells out of like natural glass. It's silica. I have a couple over here, but we also, besides they come in a whole crazy variety of shapes, but we also have had some real surprises. And this is a little fish tooth I have over here. You see that? And this is a real shocker. This is a little marine snail, a planktonic snail called a pteropod, which have got very, very delicate skeletons. But before, I was just looking at a sample from the PETM, the time period where there was extraordinary warmth that we're here to study. And during this time here, the sediments were completely filled with these tiny little diatoms. In fact, I estimate there are about 800 million per gram. Wow. So all of this that you see in the microscope are diatoms, and they come in really an amazing array of shapes and sizes. Most of them are very, very tiny. But they tell us about the environment and they tell us about the age of the sediment.
Okay, wait. Let me just translate a little bit.
Yes.
তো এখানে আমরা যেগুলো দেখতে পাচ্ছি এই অর্গানিজম গুলো, এগুলোকে ডায়াটম বলে। অলদো আমি প্যালিওন্টোলজিস্ট নই, তাও আমি চেষ্টা করছি এক্সপ্লেন করতে। তো এইগুলো হচ্ছে কাইন্ড অফ বায়োমার্কার, উই ক্যান সে, রাইট?
Well,
yeah, so
it's a fossil.
Yeah, তো সেটা দেখে আমরা বুঝতে পারি যে সেই সেডিমেন্টের এজ কি। যেহেতু এই এক্সপিডিশনটা পুরোটাই হচ্ছে আমাদের পিইটিএম বাউন্ডারিকে বোঝা, তো সেখানে আমরা দেখতে পাই যে এই ডায়াটামের নেচার এবং এদের প্রেজেন্স থেকে আমরা বুঝতে পারি যে ওটা কোন বাউন্ডারির মধ্যে পড়ে। এর আগে রিড যেগুলো দেখালো, ক্যান ইউ প্লিজ গো ব্যাক টু দ্য fish tooth and the diatom? এখানে আমরা দেখতে পাই কিছু ফিশ টুথ রয়েছে এই জিনিসটা। ইভেন আমরা কিছু শার্ক টুথও পেয়েছি। So, right? We got some shark.
Yes, this one is not a shark, but we did get some shark.
We got some, yeah. So, yeah.
And so let's go and take a look at what some of the other fossils in the electron microscope, and then I will pass you over to my colleague Hank here, who looks at organic fossils. So This is a little electron microscope, which does a very nice job of, so here's another piece of, in the electron microscope, a piece of fish, and here's that little marine snail that I was talking about. Remarkable preservation. And over here we have a lot of foraminifera. And on the inside of this one, look at this. On the inside of this one, we formed crystals of galena, which is lead ore. On the inside of this fossil, these beautiful crystals were forming.
তো যেটা দেখা গেল একটু আগে, এইগুলো হচ্ছে ফোরামিনিফেরা, যারা এখনো প্যালিওন্টোলজি পড়েনি তাদের জন্য এগুলো মাইক্রোফসিলস। এর ভেতরে কিছু ডিপোজিটস দেখা গেছে যেগুলো হচ্ছে গ্যালেনা, which is
lead ore.
Yeah, lead ore, but what is the significance of getting galena here?
There was crazy water chemistry. Some of it must have been leaching out of the basalts, I assume.
So these sediments are very near to the basalt boundary? Yes. Okay.
And these are foraminifera, which are single-celled plankton. Some live on the bottom and some live in the water column. And it's unusual to have them preserved here because they make a shell out of calcium carbonate, which in this environment usually would dissolve, yet they're still preserved here. So really rather, there's a little tiny snail. And to give you an idea of the size, this is 200 micrometers. So that's 0.2 of a millimeter in size. So with your eyes, you can just barely see a tiny dot.
Okay.
And so, yes, we have remarkable things that we've recovered in this expedition so far that tell us a tremendous amount about this very important time period when the world was much warmer than it is now. And as we try to figure out what could happen in the future if we keep adding carbon dioxide to the atmosphere, warming the planet even more than it is, warmer than we would like it to be.
Thank you so much, Reid.
Sure.
So let's go and see some other stuffs from Hank. Hello.
Hey. Yes.
So can you explain about your dinofasciites?
Oh, the dinofasciites. Yeah. So what I do is actually destructing everything that you have to sort. All these beautiful fossils. When you pour a little bit of strong acid and then a little bit of even stronger acid. In this case, HF, if that rings a bell. It's basically hydrogen fluoride, and you dissolve everything. All your problems, they go away, and you are left with a wonderful organic wall fossil. So let's compare them with, they're like a bioplastic, basically. Actually, you're looking at plastic rubbish from the past. And you can have all kinds of things that you can then find, which is all kinds of marine organisms, like you'll see, for example, here on the screen a little bit, maybe for you guys. You will see a couple of them closer by in a minute. But also all kinds of other, as you see here, dark and brown bits and pieces. And these are all fragments of all kinds of former land plants and all kinds of other, let's say, elements that you can relate to a fossil forest, for example. So you can, with one sample, you can actually reconstruct, because everything washes into the ocean, you can reconstruct both the things happening on land as well as in sea. And so you have a sort of a dual view on things. So, yeah, so what are these dinoflagellates? Let's focus on that. So just a second. So here, what you see here, and maybe you can come a little bit closer, is that when you go out here on the ship and you would have a plankton net, you can find these kinds of swimming cells, very, very, very small, but you can find them, and they have a life cycle, and in a certain point, when they want to, they decide to make a capsule with this sort of plastic bag that you see here in the lower part, and it is formed within this swimming cell wall, and then you get this plastic bag. It is sort of a reflection of this shape, and if that thing cannot longer swim, so it sinks to the ocean floor, to then basically wake up again at a certain point when it gets warmer, or when there's nutrients, or when there is some kind of trigger that them open, and you see this, and they basically swim again. So this is part of their life cycle. There's also some very nice images of this plopping thing. So you open one little door, and this cyst and the cell basically separate again, and the cyst will sink to the sea floor. And when you know which species is really occurring when and where, you can also not only tell time, but you can also tell whether we are like way offshore in the deep blue ocean, or that we are, as we are here, relatively close to land. And that's why you get also all these things coming from the land. So having said that, just to show you a couple of nice dinoflagellates. For example, here on the next slide, so they can have these wonderful spines. You see that these shapes are still reflecting the original plates of the swimming cell, and you can see there's all kinds of shapes and sizes. And if you spend a little bit more time on them, you can say, "Oh, this is that friend. I know him from 50 million years ago." And this is a very old friend, and it's 55 million years ago.
And the paleontologists are very old too.
Yeah. We are old, gray. But yeah, so and then in terms of the findings, one of the sort of interesting findings that we have besides these wonderful dinoflagellates, cysts, and you can also see them here with all these openings. These are the doors that open when the cell crawls out. But one other thing that I want to mention to you is that we also found really a gigantic amount of bits and pieces of a freshwater fern, a fern called Azolla. To see, maybe you can't read it on the screen. But this is a freshwater organism, a plant, that actually is very frequent in India. And India is actually using this because it's the fastest growing plant on the planet. There's all kinds of let's say, biological help that it can grow so fast. It can actually double its size in 48 hours. Well, not so much its size, but the amount of it, the number of specimens. And what this means, when we find so many, it means that somehow, while we are looking at an old marine or an old ocean, somehow we get this massive influx of this fresh water fur, which really is, you can find them in India everywhere. It's in ponds and still standing fresh water. And it's what it means, we think, is that it's at the time where we are looking and we are studying, and it was so warm, even warmer than in India, and it rains so heavily that you have so much fresh water that you can have a freshwater lens, which is like lighter than salt water, right? Because it has, basically, it sort of has less weight because it doesn't have the salts in it, right? So it sits on top of the salt water, even on the ocean scale, and it can grow. Plants can grow in it, and it's like a giant pond. So this is a really very interesting phenomena that basically coincides with the ending of this really super hot house that we're looking at. And so maybe it has something to do with it, because you capture a lot of carbon when you do have very many plants capturing carbon, right? But that's about that's sort of some of the things we do here, where the future is being made today.
Thank you so much, Hank. Okay, let's bye. So next আমরা যাবো chemistry lab এ। Thank you.
এখানে এই যে প্রিভিয়াস এক্সপেডিশনে যারা পার্টিসিপেট করেছিল সেখানে সেই লোগো, এখানে কিছু ব্ল্যাক এন্ড হোয়াইট লোগো রয়েছে যেগুলো অনেক দিন পুরনো, more than 40 years maybe. এখানে আমাদের ফ্যামিলি এন্ড ফ্রেন্ডস বলা রয়েছে। Okay, so let's go to the chemistry lab.
কেমিস্ট্রি ল্যাবে আমরা যেটা করি সেটা হচ্ছে প্রথমে সেডিমেন্ট তোমরা যেটা দেখলে কোর কালেক্ট হলো, কোর কালেকশনের সাথে সাথে যদি সেটা সেডিমেন্টারি রক হয় আমি উপরে যাই এবং গিয়ে 5 to 10 সেন্টিমিটারের একটা স্প্লিট আমাকে নিয়ে আসতে হয়। সেখান থেকে আমরা আইডব্লিউ ইন্ডাস্ট্রিয়াল ওয়াটার কালেক্ট করি। তো আমি খুব শর্টে দেখাবো যে কিভাবে সেই ইন্ডাস্ট্রিয়াল ওয়াটার আমরা কালেক্ট করি আর তারপর আমরা কি করছি ইন্ডাস্ট্রিয়াল ওয়াটার। আমাদের একটা প্লে কোড রয়েছে যেটা about 10 centimeters মেবি। তো এইটা নিয়ে আসার পরে এটাকে আমরা ট্রিম ডাউন করি, একটু সাইড গুলোকে আর কি কেটে দেওয়া যায়। সেটার কারণ হচ্ছে কোর লাইনার থেকে কিছু কন্টামিনেশন আসতে পারে বা সি ওয়াটার থেকে কন্টামিনেশন আসতে পারে। সেইটার জন্য আমরা কি করি, সাইড থেকে প্রথমে ট্রিম করি, ট্রিম করার পরে ভিতরের যে সেডিমেন্ট, রেস্ট অফ দ্য সেডিমেন্ট থাকে সেটাকে আমরা এই স্কুইজারের মধ্যে রাখার পরে আমরা সেটাকে এরকম বন্ধ করি। দেন এই প্রেসার যে জিনিসটা আছে সেটার নাম জানি না, সেটাকে রাখা হয়। তারপর এই পুরো সেটটাকে আমরা নিয়ে যাই আমাদের স্কুইজারে। এই জায়গাতে এসে নিয়ে আমরা এটাকে প্লেস করি সাথে এইটাকে উপরে রাখা হয়। এরপরে এখানে সুইচটা দেওয়ার সাথে সাথে ও কি করবে, উপর থেকে প্রেসার ক্রিয়েট করবে। প্রেসার ক্রিয়েট করার সাথে সাথে আমরা দেখতে পাবো এখান থেকে ড্রপ বাই ড্রপ ইন্ডাস্ট্রিয়াল ওয়াটার আসতে শুরু করে। সেটা কালেক্ট করার জন্য আমাদের কাছে কিছু সিরিঞ্জ রয়েছে, সেই সিরিঞ্জটা দিয়ে আমরা জাস্ট তাহলে যে ক্লিন পোর ওয়াটার আমরা এই সিরিঞ্জে কালেক্ট করি। তো এখানে মোটামুটি 30 ml to 40 ml আমাদের ওয়াটার লাগে। কিছু কিছু সময় এটা খুব ফাস্ট আমরা পাই ওয়াটার, অ্যারাউন্ড 10 to 15 মিনিটস। কিছু কিছু সময় এটা পেতে মোর দ্যান 1 আওয়ার সময় লাগে। সেই ওয়াটার কালেক্ট করার পরে আমরা সেই ওয়াটারকে স্প্লিট করি বিভিন্ন অ্যানালিসিসের জন্য, যেমন অ্যালকালিনিটি, পিএইচ, তার ফসফেট কন্টেন্ট, অ্যামোনিয়াম কন্টেন্ট আর বিভিন্ন রকমের এলিমেন্ট কন্টেন্ট। সো কেন এই অ্যানালিসিস গুলো ইম্পর্টেন্ট, তার কারণ যদি আমরা দেখি যে কোনো এটা করি আমরা থ্রু আউট দ্য হোল, তো লাইক 200 মিটার্স অফ সেডিমেন্টস আমরা যদি পাই, আমরা প্রত্যেকটা পোর থেকে ইন এভরি 10 মিটার্স আমরা একটা করে করে এরকম ইন্ডাস্ট্রিয়াল ওয়াটার স্যাম্পল কালেক্ট করি। যদি আমরা এরপরে দেখতে পাই যে throughout the whole আমার ম্যাগনেসিয়াম নাম্বার ম্যাগনেসিয়াম কন্টেন্ট অর পটাশিয়াম কন্টেন্ট আমি দেখতে পাচ্ছি যে এটা ইনক্রিজ করছে অর ডিক্রিজ করছে, এবং আমরা দেখতে পাই যদি ক্যালসিয়াম কন্টেন্ট আমার অপোজিট বিহেভ করছে, তো সেই বিহেভিয়ার গুলো দেখে আমরা বুঝতে পারি যে ওকে মেবি এই কোর ওয়াটারটা কোনো কারণে বেসল্টের অল্টারেশনের জন্য এফেক্টেড হয়েছে। লাইক যদি আমরা কোনো রকম ক্লে মিনারেল পাই তাহলে সেখানে আমরা দেখতে পাবো সেই ক্লে মিনারেল গুলো কি করে, পটাশিয়াম বা ম্যাগনেসিয়ামকে নিজেদের স্ট্রাকচারে অ্যাকোমোডেট করে আর ক্যালসিয়াম রিলিজ করে। তো সেখানে আমরা দেখতে পাবো সেই কোর ওয়াটারটার মধ্যে প্রচুর পরিমাণে ক্যালসিয়ামের প্রপোর্শন বেড়ে গেছে, বাট এমজি এন্ড পটাশিয়াম আমাদের লো। তো এটা একটা সিগনেচার। তো সেই রকম ভাবে আমরা যেরকম সেডিমেন্ট কোর ওয়াটারকে অ্যানালাইজ করি সেরকম ভাবে আমরা হার্ড রক অ্যানালিসিস করি। হার্ড রক অ্যানালিসিসের নিয়মটা একটু আলাদা। প্রথমে আমরা হার্ড রক তোমরা উপরে দেখলে কোর যেখানে রাখা আছে ওখান থেকে আমরা কিউব লাইক 2 to 3 সেন্টিমিটারের একটা স্যাম্পলকে নিই, সেটাকে আমরা পাউডার করি। পাউডার করার পরে সেটাকে আমরা একটা গ্লাস মানে পুরোটাকে একটা গ্লাসে পরিণত করা হয়, তো সেটাকে বলা হয় গ্লাস বিট। সেই গ্লাস বিটটাকে আমরা অ্যাসিড দিয়ে ডাইলিউট করি। সেই ডাইলিউশনের পরে আমাদের অ্যানালিসিস হয়। সেই অ্যানালিসিস থেকে আমরা কি কি পাই, বিভিন্ন রকমের এলিমেন্টাল কনসেন্ট্রেশন, লাইক মেজর এলিমেন্ট যেরকম সিলিকা, অ্যালুমিনিয়াম, পটাশিয়াম, ম্যাগনেসিয়াম, আয়রন। তো এই কনসেন্ট্রেশন গুলো পাওয়ার পরে আমরা দেখি যে কোন বেসল্ট কার থেকে কিরকম ভাবে ডিফার করছে। যেরকম ভাবে আমরা এই এক্সপিডিশনে দেখতে পেয়েছি আমাদের প্রথম সাইট যেটা, সেখানকার বেসল্টের মধ্যে টাইটানিয়ামের কনসেন্ট্রেশন অনেক লো, এখন আমরা যেখানে রয়েছি সেখানে আমরা দেখতে পাচ্ছি টাইটেনিয়ামের কনসেন্ট্রেশন বেশ হাই। তো এটা পুরো দুটো আলাদা স্যুট অফ রক। তো সেটা থেকে আমরা বুঝতে পারবো যে নিশ্চয়ই এদের ম্যান্টাল কম্পোজিশনটা ডিফারেন্ট। এবারে সেইটা ক্যালকুলেট করার জন্য অনেক আলাদা প্রসেস আছে, বাট প্রথম ডেটা পাওয়ার পরে আমরা প্রিলিমিনারি কিছু ইন্টারপ্রিটেশন এইভাবে করে থাকি। তো এই জায়গার পুরো রেসপন্সিবিলিটিটা হচ্ছে আমাদের 3 জনের, আমি আরো 2 জন রয়েছে, তো তারা আমার কাউন্টার পার্ট। তো এখানে আমরা মোট 19 জন সায়েন্টিস্ট রয়েছে, তার মধ্যে 9 জন আমরা সকাল 12টা থেকে রাত 12টা অবধি কাজ করি, এবং আমাদের কাউন্টার পার্টরা রাত 12টা থেকে সকাল 12টা অবধি কাজ করি। তো এখন তাদের অফ শিফট। তো আমি যখন অ্যাকোমোডেশনে যাব তখন আমাকে ভীষণ সাইলেন্টলি যেতে হবে, কারণ তারা নিশ্চয়ই ঘুমাচ্ছে। তো এটা হচ্ছে আমাদের কেমিস্ট্রি ল্যাবের মোটামুটি একটা ওভারভিউ। তো এখানে আমাদের এটা হচ্ছে আইসি কলোমেট্রি। এখানে আমাদের সেডিমেন্ট পোর ওয়াটারের অ্যানালিসিস হয়, আর এইটা হচ্ছে আমাদের এলিমেন্টাল অ্যানালিসিসের জন্য ICP-AES। সো এখানে আমাদের বিভিন্ন হার্ড রক আর সেডিমেন্টের যে ডাইলেশন, যে ওয়াটারটা আমি বললাম যেটা পাওয়া যায়, সেইটার অ্যানালিসিস করে আমরা বিভিন্ন এলিমেন্টাল কনসেন্ট্রেশনটা পাই। এই জায়গাটা হচ্ছে পুরোটা ইনঅর্গানিক জিওকেমিস্ট্রি। এরপরে যদি আমরা দেখি এই সেকশনটা হচ্ছে পুরো অর্গানিক জিওকেমিস্ট্রি। তো এখানে অর্গানিক জিওকেমিস্ট্রিতে আমাদের আরেকজন সায়েন্টিস্ট আছে যে এরকম কিছু স্যাম্পল কালেক্ট করে, ভীষণ অল্প পরিমাণ স্যাম্পল ফ্রম সেডিমেন্ট, সেটা কালেক্ট করে দেখার জন্য যে এর মধ্যে কার্বনেটের পরিমাণটা কিরকম আছে। তো সেটা পুরোপুরি এই সেকশনে ডিল করবে। নেক্সট, এগুলো হচ্ছে আমাদের মোটামুটি ওয়ার্কফ্লো হয়। তাহলে প্রথম থেকে হচ্ছে কোর এলো, কোর আসার পর সেটা স্প্লিটিং এর পরে আমাদের ফিজিক্যাল প্রপার্টি গ্রুপ, সেটা ডেসক্রিপশন দিল। ফিজিক্যাল প্রপার্টি গ্রুপ ডেসক্রিপশনের পরে কোর ডেসক্রাইব যারা করে তারা, তাদের মধ্যে সেডিমেন্টোলজিস্ট আছে, পেট্রোলজিস্ট আছে, তারা পুরো কোর ডেসক্রাইব করলো। করার পর যারা কেমিস্ট তারা যায় এবং তাদের স্যাম্পল যে জায়গাগুলোতে মনে হয় যেখানে আমাদের অ্যানালিসিস দরকার সেই এরিয়াগুলোর স্যাম্পলিং করে আমরা অ্যানালিসিস গুলো শেষ করে একটা কম্বাইন্ড রিপোর্ট তৈরি করি এন্ড অফ এভরি উইক অর এন্ড অফ এভরি সাইট। এই রিপোর্ট শেষ করার পর আমাদের প্রত্যেক সাইটের পরে একটা করে মিটিং হয়। সেই মিটিংটা হয় হচ্ছে আমাদের কনফারেন্স রুমে। তো এটা হচ্ছে আমাদের মিটিং এরিয়া। এখানে এখন লোকজন টেবিল টেনিসও খেলে, কিন্তু জেনারেলি আমাদের এখানে এটা আমাদের মিটিং রুম। আর এখানে কিছু বইও রয়েছে, তো কাইন্ড অফ লাইব্রেরিও বলা যেতে পারে। এখান থেকে বেরিয়ে আমরা নিচে যাবো, যেটা কিনা সব থেকে ইম্পর্টেন্ট জায়গা, সেটা হচ্ছে আমাদের ক্যান্টিন। সেখানে আমরা লাঞ্চ, ডিনার, ব্রেকফাস্ট সব কিছু করি, আর যখন ইচ্ছে তখন আমরা আইসক্রিম খেতে পারি। তো এটা হচ্ছে নেক্সট এরিয়া, আইসক্রিম মেশিন। আমাদের ক্রু মেম্বার যারা আমাদের রান্না থেকে শুরু করে আমাদের ট্রেডিং, ইভেন নন সবকিছু রেসপন্সিবিলিটি এদের জন্য আমরা খুব ইজিলি আমাদেরকে ডে টু ডে ওয়ার্ক করতে পারি, জাস্ট বিকজ অফ দেম। Very dangerous place is here. All the pastries are now. So okay, let's go to the movie room. Hello. আমরা আছি।
So first, আমাদের gene message, I guess. So why you were visiting? Even though after shift from where I it is a kind of conference room, library, movie room. So there we have a movie theater. Now আমি আমাদের অ্যাকোমোডেশনে যাব, কিন্তু সেখানে আমি অত বেশি কথা বলতে পারবো না। তো আমি জাস্ট আমার রুমটা দেখাবো, কারণ ওখানে যারা অফ শিফটে আছে তারা প্রত্যেকে ঘুমাচ্ছে, তো এটা গুড আইডিয়া নয় যে ওখানে বেশি নয়েজ ক্রিয়েট করা। সো আই উইল টেক ইট ফ্রম হিয়ার। থ্যাংক ইউ সো মাচ, Irina. Can you ask Reed? এখানে লেখাই রয়েছে। প্রত্যেকে এক একজন সায়েন্টিস্টদের রুম। Yeah, this is my small room. Okay. এখন আমরা ডাইরেক্টলি যেখানে ব্রিজ সেখানে যাব। তোমাদের যদি কোনো প্রশ্ন থাকে তোমরা চ্যাট বক্সে লিখতে পারো বা ডাইরেক্টলিও জিজ্ঞেস করতে পারো আমাদের সায়েন্টিস্টদের।
small.
Hey, Carlos. Hello, Christian.
Hello.
Can we go outside and have a chat with our students? Yeah, yeah, they will also participate, I guess. I don't know. They will also participate. So I think we have to speak a little bit louder.
Of course.
Where you want us? How do you want us?
Let's see. Let me set up the iPad first. I think everyone is visible, no?
No.
Squeeze, squeeze.
That's not a drama. Much more important.
Go, Chief.
Yeah.
Boss. No, you're not visible. Yeah, you should be.
No, you must sit next to him, otherwise.
No, here is no.
Somebody over that way.
Like the Paris peace talks, where we're fighting
sit
over
next
how
to
to
the next
arrange the table.
So we have our co-chief here, Christian, and our staff scientist, Carlos. And you already met Reed and Hank. So Carlos, can you explain a little bit how a student from master or researcher can apply for JR expedition?
Yes, can you hear me? All the way from there?
Yeah, we can hear
My name
you.
is Carlos. Okay, perfect, perfect. My name is Carlos. I'm a staff scientist with the IODP, and we're talking with India. And India is a member of the IODP program already for many years. And you can apply by contacting your program member office in India, which I don't remember if it is in Delhi, in Goa. Okay, you can apply through the program member office in Goa. And one interesting thing to do is to go to their website, and you can see which expeditions are coming up on the schedule. And they all have a call for applications, or like a time when you can apply for those cruises, depending on what the scientific objectives are going to be. If there is anything that is of your interest, and then as a member country from IODP, anyone in India who is affiliated with a university can actually sail, and it just depends on your member office to forward your names and your specialties so that we can consider you for cruises. Like we had a couple of scientists from India who had applied for this cruise.
Thank you, Carlos. And Christian, can you explain a little bit about our expedition?
Yes, sure. Yes, so this is one of the IODP expeditions that has visited this part of the world here, looking at the North Atlantic, which is a big ocean basin that opened about 55 million years ago. And during this opening of the North Atlantic, you had an enormous amount of volcanism. So and compare that basically to the Deccan basalts in India. And there are only very few episodes in the history of the Earth when there was so much volcanism as at that time when the North Atlantic opened. So if you look back, then you have this kind of episode maybe every 30 million years or so. It's a very long time. And in between the volcanism that we have today, like the island arcs and Pacific, or in the big continental subduction zones in South America, or the hotspot volcanism in Hawaii, that is much, much smaller than what happened during this opening of the Atlantic. And the goals of these expeditions are separated in different parts. The one very big objective is to understand why we get so much volcanism at this time. And there's some hypotheses around that. The mantle was very hot, and maybe had different composition, that the rifting was not like at other margins. And we try to get data to test these different hypotheses and get a big picture how you generate so much volcanism that we saw at that time. So you can imagine there were about 12 kilometers of volcanic rocks in place in some parts of the margin that is vertical. So a very, very large amount of volcanic rocks. So that is one part of the objectives, to understand how this works in the plate tectonic sense. And so what are the different drivers behind this? And then we're also looking at the consequences of this volcanism. And the time when this volcanism happened, that was one of the last periods when the climate was changing as fast as it is doing today. So we had an increase in global temperature of 5 to 6 degrees during this time, which is called the Paleocene-Eocene thermal maximum. And we want to see if there are links between this volcanism and the fast climate warming at that time. So there are lots of different ways that we can address this, and we want to understand the links between these different processes to be able to make better forecasts, basically to see what will happen in the future when we increase the CO2 content in the atmosphere that we are seeing at the moment. So how will that develop in the future? So this is basically in a nutshell how we or what we are doing here. You want to say something?
No, he's trying to block my face.
Okay. So you see, we have here Waldorf and Stadler out making comments and jokes. So yeah. There are several other objectives that we are trying to follow up to see how the climate and the ocean system was changing, like how much fresh water was coming into the North Atlantic at the time, when did the circulation patterns change in the Nordic seas. We also want to see how the breakup vessels could be used potentially to inject CO2, to get rid of CO2 that is in the atmosphere at the moment. Part of the problem of that we are facing with the global warming. And so far people try to inject CO2 into sedimentary basins, but we believe that it would be a much better idea to put that into basalt rocks, because it would be bound forever in mineral form instead of being free in the subsurface and able to get out.
Thank you so much. So if you guys have any question, you can ask directly or write it in the chat box, please. In the meantime, you can say something about our expedition, about like your experience so far.
It's been amazing. You know, it's rare that an expedition checks off the boxes of all the things we intended to do at the beginning. Usually some things go wrong. And I think we've been very, very fortunate throughout this this expedition.
Okay, I have a question from, can we classify this as ocean? Or not, you can ask your question directly.
Okay, I have a question, just a small question, whether we can consider these flood vessels as oceanic flood vessel or oceanic plateau. Is the place where you are doing this expedition?
I did not understand that. The connection was not very good.
Okay, so the question is, let me read it for you. Can we classify this as oceanic flood basalt or oceanic plateau?
Neither nor. So this is when we look at the large igneous provinces, then this one would be a volcanic rifted margin province. So that is basically when in the plume concept, the plume would hit the lithosphere and burn a hole through the lithosphere, and we would then form the main part of this large igneous province during the opening of
an ocean basin. So yeah, that is similar to the Deccan traps.
Any other question?
Okay, then it must be like a continental flat vessel, because Deccan is a continental, probably a Deccan continental flat vessel, right? Or Siberian trap. All those are continental flat vessels.
Yes, so maybe with the difference that it really formed an ocean basin, right? So the Siberian traps, that was always in a continental setting. I don't know if this is a very important distinction to make. It's basically the same process, and sometimes when the plume hits the continental lithosphere, it burns through it and starts drifting. It influences the plate tectonic setting, but the processes underneath that you have this sudden volcanism that is basically the same, and that is one of the main reasons why people believe in plumes, that you have this rapid onset in the volcanism, and if that was just a passive system with a continuous thermal anomaly in the upper mantle, then you would not expect to have these phases of very strong volcanism suddenly.
Thanks, Christian. Any question?
I'd just like to say one more thing that's remarkable about this program is we have expertise in such a broad spectrum of science, from fossils, geochemistry, hard rock, soft rock, geophysics, and everything in between, all working together, and that's really what makes the program so unique.
What is the aim of this excavation? I think our co-chiefs just mentioned that quite long. So, we want to add 2 or 3 sentences for us?
So basically, in a very short sentences, to understand why we can have so much volcanism, as we saw during the opening of the Atlantic Ocean, and what were the consequences. So these are the 2 main goals.
Okay. Any other question? Do you want to add anything, Hank?
Well,
There's another
what's really cool
question in
about
the
this
chat.
expedition is that there's some.
I was just gonna read, there's
Should we
another
take the
question in the
Yeah,
chat. Is there any opportunity for someone in computer science?
Computer science. Do you have any opportunity, Carlos, for computer science with it?
Well, I mean, when you apply for the expedition, you are also going to be required to do post-cruise work that is related to the cruise. So if your computer science can be applied to something that is geological, geophysical, it is potentially possible that it can happen. But it has to be in a field that is related to the geosciences, so that it becomes something that we can use your expertise or the expertise of that person on cruise, but also in the post-cruise research that is going to be done.
Yes, Hank, you were telling.
Well, I started to say, not only what's really cool about this expedition is that it's, as Rita already mentioned in the program, there's already everything, but already in this expedition, there's this very multidisciplinary science party, as we say. So we have so many different expertises on board because of the volcanism and the overlying sediments and the connection between them, that it is really exciting also for me, coming from the sedimentary corner of things, to learn about these volcanics and vice versa, I guess. So it's really and there's also obviously the overarching cool thing about these expeditions is that the entire ship, everybody, 24 hours per day, they work on the same scientific questions. Okay? So it's really unique in that fashion. Typically in a geological institute, you have maybe a lot of people, but they all work on their own projects or larger projects, and they work with all kinds of people, but not inside the institute. But here, everybody works on the same rock.
And we learn so much,
Yeah.
no matter how old we get.
We have another question from Devadipta. How scientists plan this kind of grand project? What are the background works involved?
Great question. That's a Kochi question.
For Kochi.
So that it's a very long. It takes a very long time to do these expeditions, and the first idea for this expedition is already 17 years old. So 17 years ago, we started to talk about this and wrote the first proposal, and this was going through the system for a very long time, and then it stopped because the riser ship that we needed for that kind of expedition was not available, and so we were put on hold, and then we could put in a new application about 3 years ago when the joyous resolution would come here to the North Atlantic. So it's normally a very, very long time to get the expedition started. And the way these things develop is through the community. So this is all driven by people who start talking about these different subjects and in different frameworks. So like maybe at the EGU meeting in San Francisco or at other conferences or through different projects and so on. And so these ideas are developing slowly. There is a possibility in Europe, at least, to do conferences. And what I did about 3 years ago was that I organized one of these Magellan workshops where 50 people were coming together and really discuss the different objectives and the state of the art for this kind of expedition in this area. From that workshop proceedings, we developed the proposal, and that was then put into the IODP system. And then it takes a long time as well, because then you have like a scientific evaluation where people look at the scientific merit. Is it really important enough to warrant like these $50 million or however much this expedition costs to do? So are you getting really important results out of it? And when they're satisfied with this, then there's another phase where this is going to the safety panel, where you have to provide a lot of data for the sites where you want to drill, and they check that it is safe to drill there. There's not gas, for example, in the subsurface that may erupt and blow up the ship, and things like this. So, and also the safety in terms of, is it sure that you will get the scientific results that you are setting out to get, and is it a high possibility to achieve the scientific result? So that is also tested at that point. And there's a bit of back and forth where you can provide new data, for example, or you can go out and collect more data if there's not enough data for some of the sites that you want to drill.
Thank you so much. We have two questions from Paleontology. So number one is from Arnav again. So do this paleoclimatology of this expedition have any implications in present day global climate change?
Yes, next question. No. Well, what is happening in the global climate today is a change that's taking place at a rate that is unknown in the geological record. We're adding carbon dioxide at such a rate, and we look in the past for analogs when things have changed very quickly. And so we've targeted this time period that we talked about before, the PETM, because that was an extraordinary warm event that took place in a geologically short period of time. It was much warmer than it is now, or warmer than it's projected to be based on the carbon dioxide we're adding now. Yet we are adding carbon dioxide at a rate even faster than this period of time, which we sort of consider geologically almost instantaneous. So in studying
this interval of extreme natural change, we can learn something about how the Earth responds to added carbon dioxide, for example. So that's one of the ways it's very relevant to what's going on in the world today.
Thanks, Reed. There is another one question is from Jeet Ganguly. As we have seen in the paleontology lab, the very small mollusca cells, so if there were microscopic molluscas present previously, and if they are present now, it's true.
Sure.
Yeah.
They don't usually preserve. It's remarkable that we have them preserved from 50 million years ago.
Okay, and then next questions from Ankush Chakraborty. How many days are these projects? So basically 2 months?
Yeah, this expedition is 65 days long. And we added to that 65 days 1 week in a hotel in Iceland for the quarantine to make sure that we were safe and that we were not going to bring any COVID on the ship. So every cruise from IODP is 65 days, and they continuously happen throughout the year.
Next question is from Tonmoy Dondopot. Is there any role of trace element geochemistry of the collected sample in this project? We got some trace element composition from geochemistry. Do you mean for hard rocks or for sediments? Yes, we got trace elements from hard rocks and from sediments, but those are not well calibrated. Okay, for hard rocks, yes, we got some, but those are not very well calibrated. So a few of them like vanadium and some titanium maybe and strontium. We are planning to do some XRF and ICP-MS analysis later after the post-cruise sample, after the post-cruise sampling party or before?
No, the XRF is before.
Yeah, and but the
are
other for XRF and ICP, what I will do, that is that will be after. And some of the samples maybe we will do before our sampling party. So not in the cruise, but yeah, surely we will get some trace element data later. কারোর যদি প্রশ্ন থাকে তোমরা বাংলাতেও করতে পারো, আমি ট্রান্সলেট করার চেষ্টা করব। What is the work of geophysicist in this project? We have a geophysicist. Yeah, it's from Ankush Chakraborty. What is the work of a geophysicist in this project? So we have Irina here, a geophysicist, and she was helping me for the camera. She was my cameraman. So yeah.
Yes, we drill in those individual points and we recover those rocks that are characterizing only that body point in the subsurface. However, in order to connect them, we need to have some additional information, and that's what we usually use geophysics for. We use seismic data and gravity data and magnetic data. That is why we study all of the physical properties, all of those rocks from the subsurface in order to link those rocks to the geophysical fields that we can record everywhere, not only at those locations. And that link allows us to interpret those geophysical data and extrapolate outside of the drilled locations. Okay. Hope I answered your question.
Okay.
Yep.
Thank you. Do we have another question? Let's see. It's already 1.5 hours now. I think so. Yeah. So yeah. So if you have any other question, তোমাদের যদি আরো কোনো কিছু প্রশ্ন থাকে তাহলে আমি আমার ইমেল আইডি অর্ণবকে দিয়ে দেবো, তোমরা সেই প্রশ্ন করতে পারো। এখনো যদি কিছু প্রশ্ন থাকে তো করতে পারো, মেবি আমরা 5 মিনিটের অপেক্ষা করতে পারি। It's already 1.5 hours. think we have any question. তো আমরা আমাদের প্রোগ্রাম মেবি এখানেই শেষ করছি। সবাইকে শুভ শারদিয়া, আর কিছুদিন পরেই
থ্যাংক ইউ সায়ন্তনী, খুব সুন্দর।
থ্যাংক ইউ সো মাচ।
থ্যাংক ইউ সায়ন্তনী, খুব সুন্দর একটা প্রোগ্রাম অ্যারেঞ্জ করবার জন্য। তোমাদের কারো যদি কোনো প্রশ্ন থাকে আমাদের যে মেল আইডিতে তোমরা সবাই এই ফর্মটা ফিল আপ করেছি, আমাদের কলেজ মেল আইডি, ডিপার্টমেন্টাল মেল আইডি, সেখানে সেই কোয়েশ্চেন করতে পারো, আমি সেটা সায়ন্তনীকে ফরওয়ার্ড করে দেবো। এবং চাইলে আমি সায়ন্তনীর মেল আইডিও তোমাদেরকে দিয়ে দিতে পারি। তোমাদের কোনো আইওডিপি রিলেটেড হোক, petrology related or any other non-geological questions, you are free to ask me or Sayantani. Thank you.
Thank you so much.
আর কারো কোন প্রশ্ন আছে? না হলে আমরা তাহলে এখানে শেষ করছি না। Thank you everyone for attending this beautiful virtual tour of IODP JIDIS resolution.
Thank you so much, Mara.
Great, thank you for the tour. It's wonderful.
Thanks a lot. Bye bye.